Hi, welcome to the Energy and Sustainability Committee webinar, how the 2015 International Energy Conservation Code will change the shape of architecture. My name is Nicole Matthews, and I'll be available to assist with most technical issues that may arise. If you have trouble connecting, please email me at nmatthews@sme.org. That's nmatthews@sme.org. Or you can call WebEx directly at 1-866-779-3239. You can also send a direct message via the Q&A box. During the presentation, please submit all your questions through this Q&A box located on the right side of your monitor and send to all panelists. Finally, the webinar today is being recorded. A link to the recording will be made available to all attendees, as well as a PDF of the presentation. You should expect to see this within 3 business days. Thank you for your participation today, and I'll now hand it over to our presenter, Kim Shin.
On behalf of the Society of American Military Engineers, I'd like to welcome you to our webinar. Not even the 3 little pigs built their houses out of glass. How the 2015 International Energy Conservation Code will change the shape of architecture. As Nicole said, I'm Kim Shin, Principal and Senior Sustainability Wizard with TLC Engineering for Architecture, your host and the presenter of today's webinar. SAMI has planned this webinar series in an effort to engage its industry members. I'd like to thank each of you for joining us today. I'm looking forward to the presentation and to your questions during the presentation. I encourage each of you to send in your questions as they arise, and I'll take them as you send them. You can type in the questions in the Q&A chat box and submit to all panelists, as Nicole said. I'll answer as many of the questions as time allows, and hopefully we'll take some time at the end to answer questions as well. After the webinar, you'll be automatically routed to a survey page. Please participate in this short poll so that we can address any concerns for future webinars. I'd like to take just a moment to introduce myself before I start the presentation. I'm a recovering physicist who got a graduate degree in mechanical engineering so I could have a reliable paycheck and regular meals. And I serve as a principal with TLC Engineering for Architecture. We're a 400-person building systems engineering, design, and commissioning firm. We have offices in Florida, Texas, Louisiana, and Tennessee, but practice all over the United States, including our offshore partners in Alaska and Hawaii. I concentrate in our energy services practice, delivering energy and computational fluid dynamic modeling for our projects, as well as for projects designed by other engineering firms. I also perform building systems commissioning, both for new and existing buildings. I personally specialize in hot and humid climates. I've been active in SAMI, ASHRAE, and the USGBC, serving on several national standards committees and boards over my nearly 40-year career. It's getting close to 50, but not quite. So the code that I'm going to be talking about today is the International Energy Conservation Code 2015 edition. This is part of the I-Code family of codes that includes the International Building Code, International Mechanical and Fire Codes, International Plumbing Code, so on and so forth. What makes this really important is the fact that the last 2 editions of the code, the 2012 and the 2015 IECC, have been huge leaps forward in building energy performance and basically have rewritten the energy code book that most of us follow as we work on our projects. And this is really pushing us toward high-performance buildings just to meet the energy code. So the 4 learning objectives that I've got for you today is specifically looking at how the architect has a role in the energy code and how meeting the energy code is really a team sport. It's not just the engineers that make the energy code work for a building project any longer. I'm going to concentrate some discussion on the prescriptive requirements that have come up in the energy code, especially the ones that have changed from earlier versions of the code. I'm going to help you understand another way to show compliance with the energy code called the performance compliance path. And then I'm also going to talk in some depth about the mandatory requirements that are part of the code that are over and above how we comply with the code on either the prescriptive path or the performance path. So once again, I want to encourage all of you to enter your questions as they come up, and I'll go ahead and take them as we go. This slide is basically the summary slide. When you get the PDF of the slide presentation and you want to say, you know, what was it that we went over and what did I learn and what are the takeaways? These are the big takeaways for you, that there are 3 ways to comply with the new energy code. We think that the performance path is the best way to comply, gives you better designs, and can cost you less money, not only in operating costs, but in first cost on the project. The second path is along ASHRAE 90.1, 2013. The third is the prescriptive path. And this is a great place to start, but we think there's better ways to engage. We also want you to know how important the envelope has been with the code. That once again, this is becoming a team sport. The building envelope, the province of the architects, is really getting some attention now in the code. And of the envelope, the windows are the most important part of the envelope. Quite simply, windows per square foot allow more than 10 times as much energy to pass through them per square foot as the wall that they sit in. And while we usually concentrate on the insulating value of the building envelope, the solar heat gain coefficient is the most important part of the window performance, especially in air conditioning climates. Now, there's a limitation, a prescriptive limitation that's now in the code that limits the window area to 30% of the overall wall area, and that those window performance factors are now certified by something called the National Fenestration Research Council. So it's really important that you understand the importance of getting that certification as you go forward in your projects, and I'll talk some more about that as we proceed. Energy modeling is a really important tool now in design, during design, not just at the end to find out if you comply, and I'll talk some more about that as well. Commissioning is now a code requirement on lighting controls for all projects and for HVAC systems on relatively modest-sized projects and larger. This used to be something that we just did on lead projects. It's now part of the basic building energy code and can be a really important element because it's now on the critical path to your certificate of occupancy. And then finally, we're going to talk about the lower lighting power densities. That's what LPD stands for, the lower amount of electrical energy that you can spend on lighting. And in order to do that, it really requires, once again, a team effort. So there's a theme here. The theme is it takes teamwork to deliver one of these projects in the new energy code. As I said, the building envelope is really important. When you look at how buildings use energy, and this is data for all existing buildings, all climate zones, if you look at how those buildings use energy, the single largest component of the building as far as energy performance goes is the envelope. Some buildings, it's more important than others, but in aggregate, roughly a third of the energy that is used in a building can be attributed to the envelope characteristics. Now, one of the things that's a challenge to us in doing projects across the United States is there's no single national energy code. The International Code Council puts out a new edition of their family of codes every 3 years. So right now the code cycles are 2006, 2009, 2012, 2015. The next one will be 2018, 2021, and so on. Most states and most jurisdictions don't adopt a new code every time that happens. They generally adopt every other code, so they're on sort of a 6-year cycle. This map that comes to us from energycodes.gov shows us the current status of energy code adoption. The yellow states are currently under the 2009 I-code group, and many of them will be switching over to the 2015 code because they're most of them on the 6-year cycle. So the states that are in green are currently under the 2015 code. The states that are in blue are on the other cycle. They were on the 2006, now have gone to the 2012 code, probably won't change their code again until 2018. So what I'm going to be talking with you today about when we get into the specifics of the code is the 2015. It's very similar to the 2012. There are a few upgrades and a few tweaks, but the 2012 and 2015 are really kind of similar. So we're going to be concentrating most of our specific comments on that. One of the things that we're seeing is that the building codes are actually increasing significantly in stringency so that they're on a track to achieve zero impact. So we've got some green building codes, things like LEED, that have sort of been out in front of our traditional building codes. We're now finding traditional building codes catching up with those leadership codes. Now, the 2015 I-codes is basically a derivation and is an adaptation and is derived from ASHRAE standard 90.1. And when we talk about this in a little detail, I'm going to show you how 90.1 fits into code compliance using the I-code. But the 2013 90.1 is the mother document, if you will, of the 2015 IECC. The 2012 IECC was derived from the 2010 90.1 version. Interestingly enough, the new version of LEED, which is version 4, their benchmark energy standard is the 90.1 2010 code. So our 2015 code that we're talking about is actually derived from an even more advanced version of 90.1. And in some cases, we're seeing projects that it is more difficult for them to comply with the 2015 energy code than it is to comply with LEED version 4, and certainly much more difficult to comply than LEED version 3 or the version 2009 versions of LEED. So here's a graph that shows you how the energy codes have changed over time. The orange line being that ASHRAE 90.1 versions, the green being the IECC versions. The very first version of the ASHRAE code came out in 1975 as a response to the very first energy crisis, the Arab oil embargo of 1973. When you look at the vertical axis, we are looking at an energy use index where a building that would have complied with that 1975 version of ASHRAE 90 would use 100 units of energy. And then as we proceed over time, you can see them decreasing as we go along, so that if we're under the 2009 version of the IECC, the yellow states in that previous slide, we're at about a 30% reduction in energy use as compared to that original code. In making the jump to the 2015 I code, we are going another 20% a reduction. 2/3 of the amount of progress that it took us about 40 years to make, we made in a single pair of code revisions. So that step is as big as we have seen in the typical 2 versions of the code that most states adopt. And that's really a big takeaway for you, is that when you look at the energy codes, any code book, you usually see a black bar along the right margin of any paragraph that's been changed. That's all that you see when you open the new 2015 IECC. There are black bars down the right margins of virtually the entire book as it goes along. So a huge change in the energy code. It's not very similar to what we've been working under, especially in the 2009 codes. The code basically gives us 3 ways to comply with it. The first compliance path is to follow the mother document, ASHRAE 90.1 2013. A lot of times we find that the 2013 ASHRAE code is more stringent than the I code, but not in all circumstances. So it's a really good idea for a project to take a look at the requirements that are in 90.1 2013 and decide whether they want to follow that path or the I code path. I'll tell you that in my experience, one of the deal killers for following ASHRAE 90.1 2013 is a mandatory requirement that receptacles that are in office spaces and computer labs, that at least half of those receptacles be on some sort of scheduling program, either through occupancy or tied to another, like, building alarm system that cuts power to those receptacles when the building is scheduled to be unoccupied. And a lot of building owners have a real problem with that. So that tends to be a deal killer for ASHRAE 90.1. That requirement does not exist yet in the international code versions. The second way to comply with the I code is to follow what's called the prescriptive path, or sometimes called the ComCheck path. And that's where you go through each section of the code and you follow to the letter what is required in each one of the sections, in the envelope, the mechanical, the service water heating, and the lighting sections, and you do exactly what's required in there. And now, for the first time, especially if you're used to dealing with the code from 2006 or 2009, there's a requirement under the prescriptive path to pick an additional efficiency package option. And some of those actually override the requirements that are in the earlier sections of the code. So imagine, if you will, an architect, a project manager tells his design team that they are to follow the prescriptive path in designing this building. And then the project goes to a code official to get a permit, and the code official says, well, I see that you've complied with all of the things that are in each individual chapter, but I don't see which of the additional efficiency packages that you've chosen. And the project manager says, oh, gee whiz, I guess we'll go with more efficient lighting systems. Well, if you wait till the job's going to permit to make that decision, that means that the lighting designer is going to have to go back in and change his lighting design to cut the lighting power densities by another 10%. The mechanical engineer is then going to have to go back and recalculate his air conditioning loads, because lighting typically is the single largest load on a mechanical system. That is a recipe for chaos. So once again, code compliance is becoming a team sport. The team needs to get together very early on and decide, if you're going to follow that prescriptive path, you need to pick out which of the 6 additional efficiency packages you're going to be designing to. And I'll talk a little bit more about what's in each of those 6 packages in just a moment. The third path, and for my money, the most effective and the most practical path, is the performance path. And the performance path actually has its own section within the code, C407, called Total Building Performance. And we'll talk a little bit more about what's in that. All of the mandatory requirements that are in each one of the subsections, the envelope, mechanical, surface water heating, and lighting sections, all of those mechanical subsections or mandatory subsections must be followed. But then what you're doing is using an energy model, building performance simulation model, to demonstrate that the building that you're designing, whether it meets any of the prescriptive requirements or not, actually uses less energy than a standard reference design building would. And that standard reference design building is more or less defined by following that prescriptive path. So it's kind of like we do when we do a LEED project. We use an energy model to demonstrate that our design is actually going to use less energy than a building that follows the prescriptive path. I'm also going to talk a little bit about the advantages of the performance path as we go along, and why that might be the best of the paths to follow. Now, it really matters where you are in following the code, because there are different requirements, especially on the building envelope, but also on the mechanical systems, about where you are in the climate zones. And there are 8 different climate zones in the United States. This shows the continental United States. Climate zones 7 and 8 are actually only in Alaska. Climate zone 8, excuse me. Climate zone 7 is limited to the rest of Alaska besides the North Slope and the very most northern regions of the Midwest and upstate Maine and the Rocky Mountains in Colorado and Wyoming. Hawaii, as well as Guam and Puerto Rico and the Virgin Islands, fall in climate zone 1A. So from south to north, the climate zones are numbered 1 through 8, and then east to west, they have a letter designation, A, B, or C. The A basically covers most of the eastern United States and is called the moist climate zone. So the climate zones there are 1A, 2A, 4A, so on and so forth. The western states are dominated by the B climate zone, once again, 2B, 3B, 4B, so on and so forth. And then on the left coast in California, Oregon, and Washington State, there's something called the marine climate zone, so 3C and 4C in those climate zones. So you can see that there's quite a bit of variety, and once again, the code requirements change from area to area. So a building designed to be in Miami can't simply be plopped down in Memphis or Minneapolis and meet the energy code. You're going to have to change those according to where you are in compliance with that. So I wanted to make a special pitch for the hot and humid climate zones because I do a lot of work there, and it becomes obvious to me, especially when I work with project teams who come out of a northern climate, that they really don't understand how important the solar heat gain coefficient is. And it is that fraction of incident solar radiation that makes it through the window and into the space as heat load. So in northern climates, we actually want a high solar heat gain coefficient. We want to let the winter sun in to give us passive solar heating in the wintertime. Down in the south, we don't want that. We want low solar heat gain coefficient numbers. So in climate zones 1, 2, and 3, we see solar heat gain coefficients that are no greater than 25%. Now, the U value, the thermal conduction value, is something that we talk about a lot in building envelopes. What it depends on is temperature difference inside and outside. It doesn't matter for U value whether the sun's out or not. It just depends on the temperature difference between the outside and the inside. And quite frankly, when you're looking at a project in the south, when it might be 95 degrees outside and 70 degrees inside, that temperature difference of 25 degrees is very small when you compare it to a project that's in Frostbite Falls, Minnesota, which is the home of Wasamatta U, the alma mater of Rocky and Bullwinkle, where it might be minus 30 outside and 70 degrees inside. That temperature difference, that 100-degree temperature difference, is 4 times greater than that summertime 25-degree temperature difference, and that means 4 times as much energy is being forced through that building envelope section that has that same U value. It's also pretty important to know that visual transmittance is very much coupled with solar heat gain coefficient. The visible light transmittance and those solar heat gain coefficient numbers, unless you do something special, tend to be very much coupled together. 25% solar heat gain coefficient usually means roughly 25% visible light transmittance. To get clearer or greater visible light transmittance and still keep the solar heat gain coefficient low means spectrally selective, much more expensive glass. Now, once again, these are values that change depending on where you are in the country, on those climate zones. And those glass selections become very critical in making sure you comply with the energy code. Now, U value is the inverse of R value. We're very much used to hearing about R value when we talk about building envelope characteristics. And this is a cross-section through a typical steel stud cavity wall construction where we've got 6-inch studs on 16-inch centers with R19 bats in between the studs, an air cavity, and then a rain screen, a brick rain screen on the outboard side. If you go along the chart here and add up the R values of each of those things as you proceed from the inside to the outside of the wall, if you add up the individual R values of each of those components, once again as you move through the wall section, if you add all those up together, you'll see that you've got a 22 value for the simple addition of all of those components. But the actual R value of that building wall, an R19 building wall, is just R11.27. And that's because of the thermal bridge that the metal studs create between the inside and the outside. And that's one of the reasons that the code is starting to require in building wall sections a continuous insulation on the outside face of the stud constructions to stop that thermal bridge that those metal studs every 16 inches on center of allowing that heat to pass through the wall section very easily. So even though this is what we might call an R19 wall, it's really in composite only slightly more than R11. And that's really important to know. So when we look at those changes between what we would typically be making the step up from the yellow states in 2009, almost all the opaque envelope requirements are more stringent. Now, the window table has actually gotten simpler, but there's now, in certain spaces, a requirement in the code for putting in skylights. It used to be that the window-to-wall ratio was 40%. It's been lowered now down to 30%. There's an exception that I'll talk about in just a second that allows you to go back up to 40%, but it really depends on doing a daylighting strategy. And now, because daylighting has been recognized as such an important energy conservation tool, daylighting, automatic daylight harvesting is now a required part of the code. So we no longer can use daylight harvesting as a way to show better than code. When we were doing lead projects under version 2009 and before, we often used daylight harvesting to get those better than code numbers that got us lead points. We can't do that anymore under the new code because daylight controls are now part of the code. I ran some energy models to help you understand the impact of the building envelope on energy performance. So what I did is I took a climate zone 2 building, so that would be roughly the Gulf Coast states, and took a 100,000 square foot, 4-story office building, 100 by 250 floor plate dimensions, oriented the 250-foot dimension along an east-west line, put 30% window-to-wall ratio, strip window, 30% window-to-wall ratio, and ran an energy model on that. And that's what we see over here in the blue, over on the far left. That is the code compliant, follows the prescriptive, the code minimum wall insulation, roof insulation, window performance factors, maximum allowable lighting power density, minimum air conditioning efficiency, just followed the code straight along. That's what that building would perform at. So let's call that the 100 line. The numbers that you see along the blue lines are actually the peak tonnage red over on the right side in the vertical axis, the peak cooling tons for that building. So in this particular case, that code-compliant building would have a peak cooling load of 143 tons. Then in this first set of bars on the far left, what I did is I increased the window-to-wall ratio, kept everything else the same, code-compliant glass, but just bigger windows. 40% window-to-wall ratio, 2/3 window-to-wall ratio, and then 90% window-to-wall ratio, essentially floor-to-ceiling glass. And you can see that the energy usage, annual energy usage, goes up almost 20% when you go to that all-glass facade. Not only does the annual energy use go up, but the air conditioning size goes up almost 30 more tons, another $60,000 on first cost on the mechanical systems alone, not to mention that the building envelope cost is going to go up because in almost all cases, windows cost more than the walls that they sit in. So by making this decision to go to an all-glass building, you're not only increasing the cost of the envelope, you're increasing the cost of the mechanical systems, first cost, and then making the operation of the building 20% more expensive year after year as the building ages. The second set of graphs that I ran are what we call the bad glass. This is glass chosen by an architect who said, you know, I really love the way that glass that I saw in that building in Vladivostok looked, so I'm going to pick that glass to put on my building. If you follow everything else in the code, 30% window-to-wall ratio, all of the other code requirements, and you just put that bad Vladivostok glass on there, you're already 16% over the annual energy use allowed by the code, plus almost, once again, 30 more tons of air conditioning. If you then make the decisions to increase the window-to-wall ratio, things go bad really fast. Look at the slope of that line as compared to the code-compliant glass, and we increase the window-to-wall ratio. Now look at how steeply it climbs, so that by the time you get to that all-glass facade, you're using almost 70% more annual energy use, and the air conditioning size has increased by 80 tons, another $160,000 worth of air conditioning cost on that building. That building on the far right, the one with 256 tons that uses 168% of the energy of the code-compliant building, that's a building that I'm working on right now, designed by another firm. We're doing the energy modeling, and we're trying to get it to meet code, and we just can't. We can't lower the lighting power density enough. We can't make the air conditioning systems efficient enough. We can't do anything to the remaining envelope, the roof, and the little bit of opaque envelope that's left on the building to bring it into code. And the architect's going nuts because he says that the building wants to be transparent. I'm not sure how he determined by talking to the building that it had that need, but he says that the building needs to be transparent. Unfortunately, we can't get him a building permit to build it because it's just using too much energy. This final set of bars over on the right is what happens when you improve the envelope. You start at code and you either shrink the size of the windows, or you make them out of better glass, or you improve the insulating characteristics of the building envelope. And you can see that while it's easy to go bad, it's not very easy to go good. And the takeaway here is that the code values that are in the building envelope tables in the code are pretty well optimized. Super insulating the roof or the opaque wall, or even getting better windows than what's required in the code does not improve the energy performance by that much. And that's a stark realization for a lot of architects to come to, that once you get better than code, you can't get a whole lot of benefit from it. It's one of those, it's hard to bring that back into compliance by doing things to the envelope. So that's the message here, is starting with an envelope that doesn't meet those prescriptive requirements is like trying to climb out of an energy hole. We've got to do things with the other components in the building, the lighting, the HVAC, the hot water, renewable energy, the opaque envelope. We have to get them so much better than code to get out of the hole that's being done by not following the prescriptive requirements in the envelope. So let's talk a little bit more about those prescriptive requirements. This eye chart that you're seeing here is actually a snip from the code that shows us the required R values for each one of the climate zones, whether the building's residential characteristics or non-residential. And then I've taken the climate zone 2, the Gulf Coast states, out and let you see what is being required there. The roofing insulation has gone from R20 up to R25, while the frame walls, metal frame above grade walls, used to be 2x4 metal studs on 16-inch centers with 4-inch R13 bats between them. Now that's had an R5 continuous insulation blue board, if you will, on the outside face of those studs. So there's now a requirement for that continuous insulation layer that we have never seen in this climate zone before. So I'm seeing a lot of architects that are used to doing business under the old code now trying to figure out how to get that continuous insulation layer on their metal studs and then hang a cladding system on the outside of that. And it's been a challenge for them. It's, once again, something they've never had to do before. For the windows, it used to be that we had less stringent U values, R values, if you will, on our windows. They're cranking down. The solar heat gain coefficients haven't changed much since the previous version of the code, but one of the things that's interesting is now the code is making an allowance for you to go with higher solar heat gain coefficients on north-facing windows. I've yet to see an architect who would actually spec different glass on one side of his building than the other 3 sides. And I tell you for sure, I've never known a contractor who would get that right. If you had 2 different kinds of glass delivered on the job site, you can make a bet that it wouldn't end up that they all ended up on the right orientation. Once again, that 30% window-to-wall ratio, this is an example of a building that meets 30% window-to-wall ratio. You can go up to 40% window-to-wall ratio if you do 3 things. And that is to make sure that at least half of the conditioned floor area is within a daylight zone, that you do automatic daylight controls in those daylight zones, and that the visible light transmittance of the windows into those daylight zones has at least 10% higher than the solar heat gain coefficient for that window. So if you were doing this in climate zone 1, 2, or 3, where the solar heat gain coefficient maximum is 25%, your visible light transmittance would have to be at least 28%. Now, this is, once again, a prescriptive requirement. the 30% window-to-wall ratio, this 40% allowable window-to-wall ratio, these are prescriptive requirements. If you don't want to, if the building absolutely has to be more transparent than the 30% or 40% window-to-wall ratio, you can still comply with code if you make the other building components more efficient than code, and that puts you on the performance path. We'll talk a little bit more about that in just a second, but this requirement of at least half of the conditioned floor area is where I got the title of the presentation. The energy code is going to change the shape of architecture. In order to get 50% of your floor area to be within a daylight zone, and it's more than a single-story building, the building is going to have to be relatively narrow. That daylight zone only extends 15 feet in from the exterior wall. So if your daylighting zone is defined by that 15-foot band next to the wall, the maximum that you could allow your building depth to be is 60 feet. 15 feet of daylit zone, 30 feet of core non-daylit zone, and then another 15 feet of daylit zone. So you can get no more than 60 feet to get the combined 30 feet of daylit zone into that 60 feet. If you're any greater than that, you're not going to be able to get that 50% of your conditioned floor area within a daylit zone. This means we're going to have much more articulated buildings like we see in Europe with courtyards, embedded plan enclosed courtyards or fingers, much more so than the big fat floor plates that we see in North American buildings. And that's once again something that our building designers are going to have to get their heads around. And that window-to-wall ratio basically is only on the above grade wall area. If you have conditioned space that is below grade, in other words, an earth-sheltered wall, you don't get to take credit for that unless those buildings have less than 15%, or those floors have less than 15% of their wall area above grade. That's a difference between the I codes and ASHRAE 90.1. Quite frankly, ASHRAE 90.1 allows you to get credit for doing earth sheltering. The I code does not. And the area of the fenestration includes both not only the glazing, but also includes the frame. It does not include opaque doors, but it does include the frame area of the window. So it's that opening. And fenestration windows are defined as something that allows light to pass through them. So they don't have to be transparent. They can be translucent. It does not include, windows do not include opaque spandrel. Opaque spandrel has to meet the requirements of the opaque wall, those R13 plus 5 continuous insulation requirements that we saw in the earlier table. So spandrel is not the same as window. It is considered opaque wall. Now, I told you a little bit earlier that one of the things that we really had to remember is how important the National Fenestration Research Council certifications are on windows. And if you have a window that does not have this certification with it, that you either don't get the calculations from the window manufacturer and or the labels that come on the windows are not there when the building inspector is doing his walkthrough of the building, then you're forced to use what are called default values. And these default values are so bad that they don't even meet the prescriptive requirements. So you're not only going to be knocked off the prescriptive path if you don't have this NFRC certification, you're going to be in an energy model and using thermal performance that is so bad it's going to hurt the performance of your energy model. So I see we've got a question. One of the questions is with this restriction in newer codes, and how are we going to be able to build high-rise skyscraper buildings with mostly glass? It doesn't seem possible. Well, it's going to be harder. It's definitely going to be harder. When we look at the outside of one of these all-glass buildings, sometimes all we see is glass as the facade material. What we sometimes do not see is that behind that glass is opaque construction, like a wainscot below the windowsill that might be 30 to 36 inches tall. On the inside, construction could be actually insulated, and then at the ceiling line where the suspended ceiling stops, that there's actually a spandrel panel that is opaque in that area. So on a 10-foot floor-to-floor building, we might see a window that starts at 4 feet above the floor, goes to 7 feet above the floor, and then the inside of those constructions above the 7-foot line and then below the 4-foot line is opaque construction. So that's a way to meet the 30% window-to-wall ratio limitation, because only the space between 4 feet above finished floor and 7 feet above finished floor is actually a window. Now, if the architect decides this building has to be transparent, it wants to be transparent. Once again, I'm not sure how architects interview their buildings and find this out, but if you have some sort of requirement that the window actually extend from floor to ceiling from 0 to 9 or 10 feet, then it's going to be extremely difficult to meet the code with that much glass, that much unprotected, if you will, glass. So once again, that's one of the things that's going to change the shape of architecture. And if you don't have those NFRC numbers, not only do you lose the ability to use what it might be a calculated U value or a manufacturer's catalog U value, you can't even use the solar heat gain coefficient number that's in the catalog for that glass. This is going to cause window manufacturers to rethink the way they do business. And one of the problems that window manufacturers have is that they have to produce these certifications for every different window on the building. So think about most buildings. They have at least 2 or 3 or sometimes dozens of window sizes. There's a 4x4 window, a 4x6 window, a 4x2 window, a 6x8 window, a 2x8 window. Every one of the windows on the building has to have a calculation done on it, because the frame area as compared to the glass area changes when you do that. And the U value doesn't simply depend on the glass itself, it also depends on the frame. Is it thermally broken? Is it vinyl? Is it aluminum? Is it colored? Is it not? All of those things come into play when you calculate the U value and the solar heat gain coefficient of a window. So it's not just the glass characteristics, it's the window assembly that has to be certified. Now, one of the things that may be a get-out-of-jail-free card on, well, get-out-of-jail-pay-$200 card is that we now see a new technology coming into the marketplace called dynamic glazing, where the glass actually can be changed in terms of solar heat gain coefficient and visible light transmittance in response to the sunlight that falls on that glass. So we could actually use some of these dynamic glazing products to lower the solar heat gain coefficients to the point where we could begin to get greater glass area and begin to approach some of those floor-to-ceiling glasses. But even at that, it's going to be difficult. And this tends to be a relatively expensive technology, adding tens of dollars per square foot to the cost of the windows. We're actually beginning to do projects with this kind of glass in special spaces like lobbies and building entrances that have a bad solar orientation face directly west, for instance, where we can use this product to allow us to still meet the code but reduce the size of the air conditioning system, and that allows us to trade off some cost that you might see on just the cost of the dynamic glazing itself. I said a little bit earlier that now for the first time in the code, we're seeing requirements for skylights in certain spaces. And if you have a space that's greater than 2,500 square foot, doesn't have, floor-to-ceiling partitions in it, so that it's greater than 2,500 square feet, that it's directly under a roof, and that it has a relatively high ceiling height, 15 feet or greater, you need to put in skylights or roof monitors such that the daylight zone covers at least half of the floor area of that space, of that greater than 2,500 square foot space. Now, and this is in a lot of space types: lobbies, assembly areas, convention centers, airport terminals, classroom, conference rooms. This is, once again, something that we've never seen in the code, a requirement for skylights. Now, one of the get-out-of-jail cards is if you have relatively low lighting power density in those spaces. So if you've got, say, like a church, a sanctuary with a really large floor area, but it has relatively low lighting power in it, you might be able to show that you don't have to put skylights there. Also, the energy savings that you would get from the daylight harvesting in those spaces is not enough to overcome the heat loss in northern climate zones. So you can see that there's an exception for climate zones 6 through 8. We also call this the big box requirement. We have seen this become part of the code because of the experience of big box stores like Walmart and Staples and Home Depot of putting in skylights that allow them to do daylight harvesting in those skylit areas and save a lot of energy. So that's, once again, one of those tactics that we used to use in LEED projects to show energy savings that we're just not seeing anymore because now it's part of the code. Lighting power densities, once again, are beginning to really descend. And once again, I'm not going to ask you to read this eye chart, but here are some of the now current lighting power densities that are going to be required under this code. So office space, for instance, no more than 82/100ths of a watt per square foot in an office building. The old code, that used to be 1 watt per square foot. So there's an 18% reduction in lighting power density in this code change from the 2009 to 2015 code. 18% reduction in lighting power density. That's huge. And once again, it's a team sport. You just can't tell your lighting designer to lower his lighting power densities because when you start lowering those lighting power densities, you've got to take into consideration what's happening in the space below. And I did a project for the Air Force on the Redneck Riviera down in the Florida Panhandle. It was a fitness center, and we had really low lighting power densities in the cardiovascular room. So we had these fixtures that hung down below the ceiling that shone light up onto the underneath side of the roof deck, and we painted it white, and the corrugated metal roof deck painted white, all of the ductwork and all of the stuff that was going to be above the lighting fixtures, we wanted to paint white so it would reflect that light down into the space and be a relatively shadow-free lighting solution. Well, the Air Force Base had a command change, and when the new two-star walked through this space when it was about half constructed, he looked up and he saw the white underneath side of the roof deck above. Sprinkler piping and ductwork was just starting to be hung in the space. The permanent lights actually hadn't been installed yet. They were just construction lights in the space. And he looked up and he said, you know, I was just in a restaurant where they had painted that whole ceiling space black so that when you looked up, you didn't see any of those ugly tubes or pipes or stuff. Why don't you do that here? And of course, when the two-star says to do something, everybody snaps to and says, yes, sir, we will. And they did. And then I got a call that when they hung the lights in the space that nobody could see, that the black ceiling just sucked the light out of the space. So I said, well, you've got a couple options. One, you can change out the lights so that they shine down instead of up. You can add some lights because we won't have as efficient a lighting solution when we do that. And we're going to have to upsize the air conditioning system because you've had to add lights in the space. Or you could paint the ceiling cavity white again. Do you know how many coats of white paint it takes to cover up a black ceiling space? So I told you that the code, if you're on the prescriptive path, makes you choose these additional efficiency package options. So there's 6 of them, and all you have to do is pick one. And depending on your building type and what's going on with some of the systems, you may or may not be able to choose lighting or additional efficiency package 6 or 7. Additional efficiency package 5 is actually to add on-site renewable energy. If you have enough roof or parking area, you might have enough PV to cover 3% of your regulated energy, or about half a watt a square foot of conditioned floor area. You're going to add between $1.50 and $3 a square foot to the project cost if you do that. A lot of people choose either package 2 or 3. They go back to the mechanical designer and say, your mechanical equipment needs to be 10% more efficient, or your lighting design has to use 10% less lighting power than is allowed by code. So remember that lighting power density that's allowed under the code for offices of 0.82 watts per square foot is now down at 0.74 watts per square foot, which is beginning to push the limits of what we can do even if we do use LED fixtures. So this brings us to the performance path. So the minute you do something to step off the prescriptive path, your window to wall ratio is greater than 30%. Your solar heat gain coefficient on your windows is 30% instead of 25%. Your You don't put economizers on your HVAC systems. Any of the things that are in the prescriptive path, you don't necessarily have to do that because now you're on the performance path. And that means you're going to have to do energy modeling. But make sure that as you step off the performance path that you look both ways so that you don't get hit by the performance path bus. So the performance path is basically using an energy model to demonstrate that the building that you're designing uses less energy than the energy cost budget method. Shows that the standard reference design uses. So you're going to compare your design against a design of the building as if it pretty much met the code, with the special requirement that you've got to reduce the energy shown in your design by at least 15%. And part of the reason for that 15% is to account for the effect of those additional efficiency packages that are in the prescriptive path. We've got a question now. Can we meet the renewable energy requirement that's in the additional efficiency path, C406.5? Nope. By using off-site renewable, by purchasing off-site renewables, and no, you cannot. It needs to be on-site. It needs to be attached to the project that you are permitting. Good question, though. So let's get back to the performance path. So the prescriptive requirements are a great place to start, but they don't always make sense, and they don't always meet what you want to do to accomplish the goals of the projects, either functionally or aesthetically, and sometimes it can be relatively expensive. So I did a project for the Army. It was a new replacement hospital at Fort Benning, and it was going to be done design build. So during the procurement phase, there were competitive teams that were going to compete not only on design solution, but also on cost for to win the project. So before we even had a final design, the contractor came to me, this was during the competitive phase, and said, okay, we've got a requirement to reduce our energy use by 30% over what's allowed by code. Do I need to put 30% more insulation into my walls? And I said, well, that's not exactly what happens when you do 30% energy improvement, but I'll look at that. So I created an energy model. Remember, at this point, we just had basically architect's sketch of what the building was going to look like, but I was able to create an energy model that allowed me to test increasing insulation in the walls of that building. So I started with the minimum energy or insulation that's required in the code on the prescriptive tables, and I ran my energy model, and then I increased that insulation by 10%. And I ran the energy model again, and the energy use actually went up. The air conditioning energy went up a lot. The heating energy went down a little. So I thought that was kind of weird, so I increased it by 15%. And the same thing happened again, is the energy use went up. The air conditioning energy went up more. The heating energy went down a little bit. The net impact was that the energy cost went up. So to test this out, I decreased the energy or insulation by 5%, and the energy use went down. The air conditioning energy use went down a lot. The heating energy went up a little bit. So what was happening is because this was a hospital with very high internal loads. Things were going on in this hospital 24 hours a day, 7 days a week, 365 days a year. Lights were on, equipment on, people in the space. That internal heat that was being generated was being trapped in the building in relatively mild fall and winter and spring seasons, as well as at night. So it was actually going to create a lower energy solution to put less insulation in the envelope. And when I told the contractor that, he was delighted because that allowed him to lower the cost that he was going to be submitting on his bid, and we won the project. The lower cost was not the only reason we won the project, but it certainly contributed to it. And we wouldn't have done that if we hadn't used the energy modeling, the performance path, to look for those solutions. So energy modeling and the performance path allow you to be project specific, look for those best solutions, be flexible in what you do in the design. So there's all kinds of different energy models. You can do energy models of existing buildings. You can use energy models to help you predict what changing operational processes might do. During the design, you can do models anytime during design, from the time that there's not even a cocktail napkin sketch to all the way in demonstrating that you either comply with code or you're getting lead points. So not one size fits all. And it's interesting to note that the modeling rules make you make some really interesting choices. So if you design your HVAC system to be packaged single zone equipment with electric resistance heat, you're going to be competing against a packaged heat pump system, which uses less energy than electric resistance heat. So you have to take that into account when you do your design. Your design might be for a ground source heat pump system. When you compete against that, you actually compete against a water source heat pump system that uses some sort of cooling tower to reject the heat rather than the earth does. So in this case, you probably have a more efficient design than you compare against when you get into your energy model. There's some things that it doesn't matter what you do in your design, you're not allowed to be any better than code, and a couple of these are pumping and fans. So you really have to understand what the rules are to know when to go after energy savings and how to go after them. Now, I talked about prescriptive things. Those are the ComCheck things. If you're on the prescriptive path, you have to follow all of those. If you don't follow something on the prescriptive path, you can still meet code by being on the performance path. Now there are some mandatory requirements, things that you have to do no matter what, even if you do a performance model. And one of the most significant of those is a requirement for continuous air barrier. In earlier versions of the code for the southern climate zones, this was not a mandatory requirement. It is now. And this is a really hard thing to add once the building is up and the code guy walks out and says, show me your air barrier. And one of the most significant ones of these is a mandatory requirement for vestibules, except in climates 1 and 2. So any of the primary entrances to the building must have a vestibule, and it must be deep enough that it's not necessary for both the interior and exterior doors to be open at the same time in order to get through the space. So it's I've talked once again to a lot of building designers that say, oh my gosh, I'm going to have to give up floor space in my building entrance to accommodate this vestibule. This is not something I was counting on. And once again, because it's mandatory, you can't use an energy model to get out of it. This air barrier requirement goes throughout all of the climate zones except for 2B, the desert Southwest. And there are 3 ways to comply with the air barrier requirement. One is to make your building envelope out of nothing but materials that meet the ASTM E2178 permeate standard. Or you can construct the envelope out of assemblies of materials that have been tested by these 3 ASTM standards. Or you can make it out of anything you want to, as long as you can pressure test the building to show that it doesn't leak more than 0.4 of a CFM per square foot of building envelope area when subjected to a 0.3 of an inch water, or 0.3 of an inch of water gauge pressure difference on the building envelope. Now, this third option is something that we've started to see in residential construction. This is the first time that we've seen it in commercial construction. Imagine, if you will, how difficult it would be to construct a building that's multi-story with big floor plates, lots of floor-to-floor openings like stairwells and windows. It's going to be really hard to do that. Going back to our friends at NFRC, if you don't have NFRC certification on your fenestration, you're going to have to pressure test the building. That's the only way to demonstrate compliance with this mandatory requirement if your windows don't have that NFRC certification, and this includes curtain front and storefront, curtain walls and storefront. There are very few current curtain wall manufacturers that are producing that certification. And once again, if you don't have that, then your only option is to do air barrier, your pressure testing of the building. There's now a requirement for demand control ventilation on relatively low occupancy spaces. So it used to be that any space that had more than 40 people per 1,000 square feet and was over 500 square feet, you could have to do demand control ventilation. In other words, modulate the amount of fresh air that goes into the space in response to the number of people that are in it. That number has gone down significantly. It's down to 25 people per 1,000 square feet. This essentially means every classroom and conference room and break room now has a mandatory requirement for demand control ventilation, unless you have those exceptions. There's another mandatory requirement now for energy recovery that divides whether the building is operated 24/7 or not. So it is pretty common to see air conditioning systems that have about 25% outside air at full supply demand, so that fall into this category here. If you're in the Gulf Coast area, 2A and 3A, and your air handling system has a supply flow of more than 16,000 CFM, then you're going to have to put energy recovery on that system. Now, a 16,000 CFM air handler is a box that's about 6 feet square. I mention this because this is going to have impact on mechanical room sizing. because the energy recovery equipment that goes with a box that's about 6 feet square is another box about 6 feet square. So you're either going to be putting in a lot of smaller systems to get away with not having to put in energy recovery, or you're going to have to increase the mechanical equipment spaces in order to accommodate that. If you have a 24/7 operation that's operating at more than 8,000 hours per year, those size requirements have gotten really small. So basically, anything bigger than a big fan coil unit is going to have energy recovery on it. And this is not that much outside air. So once again, stuff that we've not had to do in the past is now mandatory. Electrical lighting power, we've already seen that's gotten more restrictive. We've now got a whole lot more mandatory lighting controls. Occupancy sensors, time switch, lighting reduction, where we do the ability to dim or shut off part of the light in a space, as well as these automatic daylight responsive controls. Once again, stuff that we've never had to do before. This is going to catch a lot of electrical designers by surprise. Spaces that they've not been doing daylight harvesting in the past, now mandatory. There's a few exceptions, but once again, any light that falls within this daylit zone is going to have automatic daylighting controls on it, stuff that we've never seen before. Exterior lighting is now got very similar to the way that we do it in LEED, where it's sensitive to whether you're in an urban zone or a rural zone. There's now a requirement that facade and landscape lighting have midnight to 6 a.m. shut off. It used to be that those lights ran all night long. Now they have to shut down or reduce output in the midnight to 6 a.m. hours. Once again, mandatory. You don't have a way to get out of this by running an energy model. So I mentioned this before. Once again, commissioning is now required by code. This is not just something that we do for LEED projects anymore. This table shows what we do for LEED. This is all the stuff that we would do for a LEED project. The highlighted ones are now code required. These are things that must be done to meet the code. No exceptions, no getting out of jail free card for where you are in the country. None of that. Now required for all projects. On mechanical systems, it's if your building system has 40 tons of air conditioning or more. For service water and lighting controls, it's all buildings. Must be commissioned. You've got to put the requirements for commissioning in the set that goes to get a permit. So no more waiting till the project is almost complete in construction to do commissioning. The commissioning plan, who does the commissioning, what's going to be commissioned, how it's going to be commissioned, needs to be to get a permit. You must complete the mechanical or the commissioning to at least a preliminary status, identifying any critical path items before acceptance. There will be no mechanical final inspection done until the owner receives the preliminary commissioning report. And then it even continues post-occupancy. There must be final reports given to the owner and deferred system testing 6 months on after the building is occupied. So all of this must be submitted to the owner. I don't know how a code official is going to enforce something after the building is occupied, but that's what it says in the code now. Now, I can't emphasize this enough. You can't pass the final mechanical inspection without a preliminary commissioning report. So imagine, if you will, everybody shows up on Friday, the owner's going to move in on Saturday and occupy the building on Monday. The code official walks up and says, okay, where's the preliminary commissioning report before I can do your mechanical final inspection so you can occupy the building? And Bubba turns to Billy Joe and says, where's my commissioning report, Billy Joe? And Billy Joe turns to Bubba and says, what's commissioning? So, one more time. You can comply by following ASHRAE 90.1 2013. You can comply by following ComCheck and the prescriptive path, or you can use energy modeling to demonstrate that your building uses less energy than is required by a code-compliant building. And once again, it's all about teamwork. So I'd like to take some questions for you now. Please go ahead and put some questions into the question box. So I'll give you a few minutes here to come up with those questions. We've got a question about, so how does this code relate to the DOD's commitment to reducing energy use? Well, right now the Energy Independence and Security Act of 2009 requires a reduction of energy use below ASHRAE standard 90.1. I think it's been upgraded to ASHRAE 90.1 2010. So this code is not quite as stringent as the DOD requirements, but it's quickly approaching that point. So even if you're not doing DOD work, you're going to be doing stuff to demonstrate that you're doing a lot less energy consumption than you used to be. Another question is, when should a project follow the prescriptive path instead of the energy modeling-based performance path to demonstrate code compliance? I would say that that's almost never the case. You almost always have to do energy modeling because the code under the prescriptive path has gotten so restrictive and in some cases so expensive that you can almost always use an energy model to produce a building that costs less money to build as well as uses less money to operate. Another question has come in, have any of your building energy costs matched the energy model? And I have to tell you that no, they don't, because energy models do not predict operational cost. And the reason that they don't is because energy modelers cannot predict the future. If energy modelers could predict the future, we'd all be incredibly wealthy because we would predict what the lottery numbers are going to be, and there would be no energy modelers. We cannot predict what the weather's going to be, and we cannot predict how the building's going to be constructed and operated. What building energy models are good at doing is comparing one design against another. Energy models are really good at saying this is this many percent better than that. They are no good at predicting the actual energy use of the building. Now, what we can do with energy models is once buildings start to operate, we can then take the actual operating characteristics of the building and the actual weather files and calibrate the energy models so that they reflect that actual set of weather data and operating characteristics. and we can actually use that to then test different operating strategies or perhaps different energy conservation measures like more efficient mechanical equipment or lighting controls or even a building envelope retrofit to predict energy performance then. But energy models are very bad at predicting actual energy consumption. So, anybody have any other questions? We can hang out for a few more minutes and answer some more questions. You know, there's few enough of you on this call that I could actually point to you and ask if you have a question. Don't make me do that. Going once, going twice. All right. I want to thank you all very much for attending this afternoon. On behalf of SAMI, we appreciate everybody's participation and hope that this webinar has been useful. If you have any additional questions, please submit them via email to Nicole Matthews at nmatthews, M-A-T-H-E-W-S, @sami.org. And that concludes our webinar. You may now disconnect and have a wonderful day.